I'm pleased to see some people are still here. I checked yesterday with some of the students who have now gone back to Sweden about the level, and apparently it's okay. However, I heard I should slow down from some people. So in any case, I was worried I was going too slowly, but I guess I'm not. But that's going to renormalize what I'm going to do. Of course, today you can tell me I went too slow, and then tomorrow I can speed up. But so I'm not 100% certain of what I'm going to cover in the last part I'm pretty sure of what I'm going to cover today. But tomorrow I'm not so certain. Remember, this was the outline I put up yesterday. And we are going to get through here, and in fact, I've decided to go into some detail in the age of the universe to give you an object lesson in the potential pitfalls of doing an astrophysical constraint on particle physics, because I think there's a lot to be learned from there. So at the beginning of the next lecture, I'm definitely going to discuss some of the limits you can get from stars on axions and things, because it's quick and I think it's also interesting. Then which of these topics I cover, I'm not 100% certain. I know what I'm leaning towards, but I thought I might get some audience participation. And see, I'm sort of leaning towards leaving out solar neutrinos only because I find them very boring. But I don't know if there's any, also because, if you've heard a talk on this in the last 20 years, nothing has changed in my opinion. So I don't know if there's any strong objection to any of that or any strong preferences. Maybe you can just look at this and tell me after the lecture if you want those things you would particularly like to hear, and I can't guarantee I'll do any of them, but I might do some of them. So I will do some subset, but I'm not going to rush because there is no fixed agenda here. I will definitely do the issue of the baryon catastrophe, because I think that's an important issue, and I will cover that tomorrow, and some subset of other things. I'm also leaning against galaxy, COBE in particular, because I think that's because it's such a current topic that it's hard to go anywhere and not hear a seminar on it, and therefore it may be something that is easily covered. Since I've been here, there's probably been 4 seminars or 5 or maybe 6 on COBE-related issues, or CMB-related issues. So I may leave that out as well, only because you can hear it elsewhere, in spite of its obvious importance. You can also pass down the assignments I handed out last time. Okay. What I want to finish today is the issue. Remember, in the last lecture, I got to the issue of particle dark matter and described the 3 mechanisms for producing it, which are really quite different. It's quite remarkable that such different mechanisms can produce dark matter candidates that are indeed so different. The axion, to be dark matter, it would be around 10 to the minus 5 electron volts. A monopole, magnetic monopole, on the other hand, could be greater than the Planck mass. And that particles that are so different in terms of also their interactions, and a magnetic monopole interacts electromagnetically, clearly, and an axion interacts extremely weakly, that these particles with such different interactions can still have natural production mechanisms in the early universe, which would make them dark matter. And I remind you that for each of them, those mechanisms, in particular WIMPs and axions, those particles were discussed before it was discovered they could be dark matter candidates. In any case, so they're quite different, but it is equally heartening. I rewrote this transparency to make it a little neater from yesterday, that each of them has a direct signal. And so what I want to do in the first 20 minutes or half an hour is discuss the signatures for each of the dark matter candidates, just so you can see the kind of experiments that are going on. And to give you an idea of how while they each have signals, except for the neutrino, as I said, but that's okay because we don't think the neutrino is the dominant dark matter in the universe, as I showed you the galaxy clustering diagram yesterday to convince you that at least on a computer, neutrinos do not make a good universe. But the signals are small, and I just wanted to remind you how much they differ. In an axion detector, which I'll show you, the average energy per event is 10 to the minus 5 electron volts. The power deposited in a detector is 10 to the minus 24 watts per cubic meter, which is small. A WIMP detector will detect energy events deposits between, say, 10 and and 100,000 electron volts, the energy deposited at best is something like 10 to the minus 19 watts per kilogram. And just to remind you, I tried to pick a number to normalize. The radioactivity in your big toe is 10 to the minus 12 watts, okay? Which is either, therefore, 7 orders or 12 orders of magnitude larger than the kind of signal you're trying to detect in these detectors, which means that while their signals are there, it's not so easy. But I just want to remind you, and for the younger people, give you a little history, maybe because in particular about monopoles. One doesn't hear much talk about monopoles as dark matter anymore. I know why, but I'm not so convinced that it's correct, that thinking. So that's why I wanted to remind you a little bit about the kind of ways of detecting them. The ways of detecting monopoles are based on 2 different things. First of all, monopoles being magnetic charges, when they move, produce a magnetic current. And that means they produce a unique signature in any loop of wire. Okay? And that was the way the only monopole in the universe was first discovered, as I'll show you. The other possibility is that if they're moving fast enough, because they interact electromagnetically, that they might ionize in some sort. And therefore, one can look for them in scintillators. And that's the other constraint on them. The advantage, of course, of any kind of monopole detection scheme is that monopoles of all the particles are the only ones that interact with any kind of strength that's significant electromagnetically. The disadvantage, however, is that monopoles of interest have a mass which is very large, and therefore a flux which is very small if they're going to not overclose the universe today. And therefore, while the interaction strength is very great, the rate is very small, and one has to build big detectors. So let me just remind you, I have some pictures or at least a discussion of some of the experiments, and then I want to briefly mention some of the indirect constraints, but without giving you figures or numbers, because I think I forgot to prepare that transparency since I wrote that. I just want to remind you of the idea which was first used to look for magnetic monopoles, which is really quite pretty, and that is that a magnetic monopole, of course, being a source of magnetic current, when it goes through a loop, in particular a superconducting loop, will produce a persistent current by the laws of electromagnetism extended to include magnetic currents. And what's important about this is that a magnetic monopole that does not traverse the loop will produce some small perturbation, but there'll be no current left. And only a monopole which goes through the loop will produce a persistent current. And the current, of course, will be independent of the direction of the monopole as long as it traverses the loop, just by topology. So we'll get the signal for a monopole coming in and nothing otherwise. And just to remind you, on Valentine's Day in 1982, Blas Cabrera, in an experiment which is, no one has ever still explained this event convincingly, had a signature which is remarkably remarkable. In a superconducting loop in the basement of the Stanford Physics Department, had a signal which looked like that. And this is you can see the small perturbations when you put liquid nitrogen in a thing, or if you hit it with a hammer, you can produce small perturbations. But what was particularly scary about this is that the jump was not only quite clear, but the magnitude was exactly that predicted, I think, for a Dirac magnetic monopole. And so it was very exciting that day. Unfortunately, as all of you know, there hasn't been any other events. However, it is interesting that one of the predictions of inflation may be that there is one monopole in the universe. And so those proponents of inflation may say this is yet another clear evidence in favor of that theory. But in any case, the largest fully man-made detector, and unfortunately these experiments I went searching on the net. I have, as I told you before, all the transparencies which would be relevant for most of this in the United States, where they were before I came here and before I was asked to do this series of lectures. But I could find an old figure that I had. But of course this is macro before it was completed. It's been completed for some time now, but I couldn't find a figure on the net to download. But this is one example of a detector which is used for many things, of scintillator and iron, and basically look for ionization, not in materials. There are other detectors, and there's Lake Baikal and other places. There are detectors on monopoles, and these things are very big. And the idea of the monopole detectors is to make them very big. The signal is easy to see in principle. It's just that it occurs so rarely. The flux is so small. And to give you an idea, here is some constraints. You can look for signatures not just in this detector, but in any big detector, IMB, Kamiokande, any big place will see monopoles if they go through, because they ionize, in principle, depending upon their velocity. And so one can look at constraints that exist on monopole fluxes as a function of their velocity. And here is one compilation. I have another compilation from Macro that I got off the net. But the thing is, what's interesting is that, of course, these bounds shown here are not unfortunately, the theoretical constraints, but these bounds are very severe. As you can see, they're constraints on the flux of something less than 10 to the minus 16 per centimeter squared per second per steradian, which is very small, and that's one of the reasons people don't talk about monopoles anymore. The other reason is that there are other indirect limits on monopoles, which for many masses of monopoles would make them irrelevant for dark matter. The most interesting one is the so-called Parker bound, which is quite simple. Monopoles like to follow magnetic flux lines and eat them as they move. And so the galaxy has a magnetic field, and monopoles, if they're moving slowly enough or if they're light enough, will in fact, the predominant force they will feel in the galaxy is not gravity but magnetic field strength, and they will follow the magnetic field lines of the galaxy and eat them. And as a result, they will destroy the magnetic field of the galaxy. And that is these are the constraints on their flux, so that the galaxy has been able to keep its magnetic field. There are similar, and indeed sometimes stronger constraints, depending upon what you believe, on the nature of magnetic fields of neutron stars, for example, also where monopoles will go through neutron stars and eat the magnetic field lines and such. And in fact, also certain types of monopoles have very strong constraints because they might catalyze proton decay, which I won't talk about. And in which case they're very strong in constraints. So that's why you don't see discussions of this anymore. You have the people who of course look for them, publish papers on it, but those are the only people that seem to talk about it. Here's a macro constraint, which also not only looks for monopoles, but dyons, which are particles that could not just have magnetic charge, but electric charge. And there are similar constraints, and this will be the full macro constraint, and I may have already, it will be again around for the full value of beta around 10 to the minus 16. The reason I just want to leave you with a little bit of heresy, why I think monopoles are still interesting, is when monopoles were first discussed, they would naturally arise in many grand unified theories when you spontaneously break down to a final U1 from some non-abelian group. Therefore their mass is of order 1 over alpha times the symmetry breaking scale. And people therefore looked for magnetic monopoles that might be 10 to the 17th GeV or so, because the grand unified scale was thought to be around 10 to the 15th or 10 to the 16th. But it seems to me, in fact, that it's far more interesting to think of monopoles of late, which might be related to the Planck scale or higher. There's been a lot of interest, in fact, in magnetic charges associated with black holes and whether they might stabilize black holes of certain masses. And therefore, I tend to think, while it's not very current or au courant in the dark matter world, that a much more likely scale, if monopoles exist, might be of order the Planck mass over alpha. And I think on this scale, I put I calculated that the flux of Planck mass over alpha black holes, anyone can do the calculation, which will lead to omega 1 is, of course, conveniently below the existing bounds. So I tend to think that it's worth continuing to think about monopoles, even though they probably don't. Any monopoles associated with grand unified theories, at least as dark matter, are certainly ruled out. Okay? That's all I'll say about monopoles. The next, and I'll spend much more time, because I'm at CERN, on the signature for WIMPs, because of course they relate to the particles that are proposed. The lightest supersymmetric particle might be, as I argued in my last lecture, a WIMP. And the idea behind direct detection is quite simple. The first is that since of all the dark matter particles, WIMPs are the ones which have the closest mass or we might say impedance match to the mass of normal matter. When a WIMP scatters off a nucleus or a proton, one can think of it as a billiard ball collision in the sense that the masses are comparable, so it's quite efficient for energy transfer. As you know, a particle can transfer its, can lose half its energy in a collision like this, but it depends on what, as I said, is the impedance match of these masses. If the masses are very similar, it can lose a lot of energy. As the masses become very different, either one mass becomes much bigger than the other, or one mass becomes much smaller than the other, the kinematics tell you that basically the maximum energy transfer is related to the ratio of masses. And so that this becomes a not very efficient mechanism for transferring energy. But if they're comparable, you can do that. Now, if you think about the amount of energy characteristically transferred by such a particle, a WIMP traveling in our galaxy will have a characteristic velocity of our galaxy of about 10 to the minus 3 c or so, something like that. And therefore, its kinetic energy will just be its mass times v squared approximately, which is therefore about 10 to the minus 6 times its mass. And if you're in the GeV range, then you expect a kinetic energy in the keV range. So the maximum kind of energy transfer you're ever going to get in an elastic collision in this range is in the tens of keV or hundreds of keV, depending upon the mass of this particle. And now, since, as I argued earlier, or mentioned earlier, and I think I'll explicitly discuss, the light supersymmetric particle constraints are probably in the range of 20 to 30 GeV now. That means that you're talking sort of 20 to 30 keV as the kind of energies potentially. Now, what really made this quite interesting was the observation, I believe first by Goodman and Witten, that for Dirac neutrinos in particular, which at that time were the prime candidates for WIMPs, the cross sections for scattering are very similar to the cross sections for annihilation. If all the masses are approximately the same, the cross section by dimensional analysis will just be gm squared again, just like it was for annihilation in the calculation I showed you yesterday. As long as the masses are all of order the same, then that is the only dimensional quantity that can appear there. But what was recognized is that neutrinos, this has been well known for a long time, although it is yet to be measured ever experimentally, neutrinos have coherent interactions, Dirac neutrinos do, by Z exchange. The neutrino can coherently interact off the entire nucleus, off the entire weak charge of a nucleus, depending upon the momentum transfer. And therefore, the cross-section for coherent scattering of neutrinos can be much larger than the cross-section for just scattering off single particles. If there are, this is approximately the number of neutrons in a nucleus, depending upon, again, it depends upon, well, in the neutrinos it's fixed. It's just the weak charge. And therefore, if you have a large nucleus, you can have a cross-section which is enhanced by a factor of 10,000 compared to standard neutrino interaction rates. And this is very interesting. And as I say, it's never yet been measured for regular neutrinos, but it might be relevant. It's one of the ways you might be able to put a large constraint on things like magnetic moment of neutrinos. But in any case, that's a different subject. The point is that because of this, you get a large interaction rate. And this caused a lot of interest initially. The problem is that if the particle is axially coupled and not vector coupled, you can show that what it will couple to is some, I should add some other quantity in here. Well, since I have an approximate, it doesn't really matter. I'll put a k here. Depending upon the exact interactions of the particle, it will interact with gm squared strength, but now relative to the spin of the nucleus. In fact, the spin of the valence nucleon. When this first got proposed, people decided to do experiments, and I still hear people talking about doing experiments with large spin nuclei, but of course that's irrelevant, because most of what people call the spin of the nucleus is angular momentum. And what you really care about is the spin. So you having a nucleus with spin 9 halves doesn't do anything for you. All you need is a nucleus with basically an odd number of nucleons in it, and then there's some nuclear corrections, which I and other people have calculated. But the point is, this is much smaller than that. And the rates for these interactions, if you calculate it's remembering the magic number of roughly 1 GeV per cubic centimeter as the WIMP density predicted in our region of the galaxy. Just plugging in a WIMP mass, you can get the flux, and then you can get the rate. And you find that the rates are much less than a kilogram per day in the keV range. So how do you do that? This initially looked like it might be, again, kind of impossible, but it was recognized that already low background detectors were being built. In particular, at the time this was first discussed, there were already existing low background detectors to look for one of the lowest background processes around, which is double beta decay. Germanium detectors were specifically built with very low backgrounds to look for events in the MeV range, but it was realized that for some of these detectors you might be able to push them down to the keV range and actually look for a signal. What would you look for such a signal in a germanium detector originally is ionization. When this scatters off this, it hits the nucleus moves and ionizes. The problem is, of course, that as the energies get very small in the keV range, the nucleus moves slower and slower and slower. And in fact, if you did a classical calculation, which I remember we sort of did when we first thought about this, you will predict that the nucleus won't ionize at all. But in fact, it does. It turns out, and people have done calculations on this, more sophisticated calculations, that right down to low energies, the nucleus will ionize, but not very efficiently. The amount of ionization will be reduced as it goes slower and slower. And this will be an important signature in a second. But what was also recognized that a much more efficient signature might come from phonons rather than ions, because as the nucleus goes slower and slower and slower, it deposits in a crystal lattice its energy much more effectively in lattice vibrations. And in particular, what appealed to a group of us when we thought about it a long time ago is that if you think of materials like silicon, the specific heat goes down very rapidly as you cool the material down. And therefore, you will find that you can get a macroscopic temperature change in a material for even a microscopic amount of energy deposited. And this was quite intriguing. Those principles have led to a bunch of detectors, which I will discuss. Which I'll discuss in more detail in a moment. But let me also indicate there's another interesting signal. And that was, I remember this is the only time I actually really believed that WIMPs existed for a moment. Did a rough estimate and realized that given the weak interaction cross sections, how big a target would you need to have a mean free path of order the size of the target? You can find it's about the size of the sun, the mass of the sun. And in fact, therefore, WIMPs will be captured or will be scattered in the sun. And since the escape velocity from the sun at its surface is somewhere near the orbital velocity in the galaxy, scattering could easily lead to capture. And so WIMPs in principle could be captured in the sun, depending upon, again, the problem is the sun is made mostly of hydrogen. And in those days, when WIMPs were around 2 GeV, that was great for scattering. But hydrogen is not so efficient as capture of things which weigh 100 GeV or 50 GeV, just because of that impedance mismatch again. But you might expect that they will build up in the sun. In fact, this was originally proposed once by a group of people to suggest a way out of the solar neutrino problem. That didn't survive very long, not just because it won't solve the solar neutrino problem even if it could happen, but for any realistic particle it could never happen. And the reason was that any realistic particle will build up, and then once its abundance becomes large enough, particles and antiparticles will be captured and they'll actually annihilate in the sun. And you will eventually reach an equilibrium level in the sun where the annihilations equal the capture rate, and then you will not build up any more abundance of these particles in the sun, and you will not build up a big enough abundance that these particles could efficiently allow any kind of energy transfer from the core to the outside. But among their annihilations are particles like neutrinos. And if these particles therefore are in the tens of GeV range and they annihilate to produce neutrinos, you would expect the sun to be an efficient source of 10 GeV neutrinos, which you can look for, of course, in large underground detectors. Moreover, not only the sun, but also the Earth would allow this capture rate. In fact, for massive particles, because of the impedance mismatch, for a certain range, the Earth can be an efficient capture of dark matter as well. And again, you can look down at the Earth from these things and look for a signal coming from the center of the Earth or the center of the sun. And there are, of course, vast backgrounds, but if you're looking for a small solid angle, you can try and beat the backgrounds, in principle. What is particularly interesting about this and nice is that all of this is fixed. The same cross-section comes in 3 different times for capture, and for annihilation, and the same process that produces the WIMP in the early universe. Remember, I did the calculation last time for you with the Boltzmann equation to show you that the WIMP abundance in the universe today is specifically determined by its annihilation rate in the early universe. So there are no free parameters here, which is particularly nice and also particularly unusual for any kind of cosmological or application of particle physics. Everything is fixed. If you tell me the abundance of these things, it's based on its annihilation rate, and one can determine the capture rate and therefore the annihilation signal. So you can look for these indirectly in any kind of detector that can look for high energy neutrinos. And there are many such detectors: macro, super Kamiokande, IMB, etc. Well, let me just show you the kind of detectors that look for dark matter and briefly describe their properties. Again, I couldn't find a picture of any of the new ones, but I found a picture of the old one, which is the original. This is a germanium double beta decay detector, which is used to look for double beta decay, very pure germanium. But it was also used initially. It was realized that, as I said, the backgrounds could be pushed down to the KeV region to give constraints on WIMP dark matter, which I'll come back to. Because I want to show you that one of the reasons we're talking about this is it shows you a prototypical example of the symbiosis that can happen between accelerators and non-accelerator physics. And I want to just show you one of the few cases where at least where it's obvious that there was such a symbiosis. But there are many existing low temperature detectors here, and so I won't offend people. I put a list of them. They're all cryogenic here. They all depend on sort of the crystal structure. Some of them look for ionization. Some of them look for phonons and ionization. Their masses are approaching, in the case, some of them have already approached the kilogram range, which is the kind of canonical value to for looking for potentially measurable signals, and the backgrounds have been pushed down. And so what are the signals? Well, as I say, the first signal that was proposed was just simply that you put a chunk of silicon or something like it and hook a thermometer up to it, and when a neutrino, or a WIMP particle, or neutralino now I should say, were to go through that, it might deposit several tens of keV of energy. You can calculate that that will heat the whole thing up by a millidegree Kelvin, if it's a kilogram of material when it's cold, which is really kind of remarkable that such a low energy event will heat up such a macroscopic amount of material. And you look for a thermal pulse. The problem, of course, with that is one of the problems that this thermal pulse is fairly long, hundreds of maybe milliseconds or so, and if you're interested in cutting down backgrounds, it's a long pulse. Something that was realized quite quickly is there's no reason to wait for the temperature to thermalize. The temperature thermalizes in the crystal by phonons being produced and then thermalizing. But the phonons themselves travel ballistically early on, and therefore will go to your detector, and you can look for a pulse, which is not a thermal pulse, but actually the ballistic pulse of phonons, which happens in a much shorter time scale, and therefore is much better from the point of view of blocking out backgrounds and such. I put these other wires here because at the same time you also might want to look for ionization. And I'll come back to that. Anyway, so one of the other nice things about crystals in principle, which hasn't yet been exploited, is that that the dispersion relations are different in different directions along crystal lattices. And so this is an example. This was a calculation in a chunk of silicon of producing ballistic phonons from an event somewhere in the middle, in the signal that you would see if you had detectors all around this chunk. If you put stripped detectors to detect the ballistic phonons that came out, you'd see they'd come in specific directions because of that anisotropic propagation velocity, and you'd be able to extract, for example, in this case, exactly where the event occurred. Which, if you're looking for things that trying to get rid of impurities on surfaces, this is quite interesting. This has been also demonstrated not just Monte Carlo, but in practice. People actually can do this, and there's at least one group that's trying to use this, I think, in their dark matter detection apparatus. Okay, so let me see what I got here. Well, let me just show you the kind of constraints that come from these detectors, and just to remind you, this is one of the many things that people are trying to get down. You're trying to look for energy in the keV range, and you're trying to cut down to an event or less per kilogram per keV per day, and this is one of the detectors. And you see what happens is that you have a wall here. You can work very hard to get rid of radioactivity here, but you tend to have a wall coming from lots of stuff here, including just detector noise. And so the level of this wall will determine the efficiency of your constraints on dark matter particles. Because if you see no events here, and you have very little background, you can put constraints, but eventually they'll all go away, and you see that the range at which they're going to go away is in the keV range. And that means all of these kind of detectors are going to disappear in their efficiency of constraining dark matter using v squared being 10 to the minus 6, in the GeV to 10 GeV range. And so here's an example of the kind of constraints that already exist. I have a few different examples, but they all look the same. If you're trying to constrain events per keV per day, you see that what happens is, if you look at a WIMP mass, that here's the presently excluded range from one experiment, but as I say, they all look very similar. I think I have another one somewhere else. Yeah, I do. Maybe. Okay, well, this one will do. And all those constraints go to hell when you try and get to a mass less than about 10 GeV. Okay? But what's interesting here is that you notice that already these experiments could rule out a heavy Dirac neutrino as dark matter. This is 10 years ago, down to about 10 GeV or so because of that. This would be the reaction rate. What's important, of course, for these detectors is, and this was an optimistic estimate based a few years ago, the actual kind of WIMPs which are well motivated today come from supersymmetry, neutrinos, and their interaction rate is much smaller for two reasons. One, the masses are getting pushed up by LEP and other places that haven't seen them. And also, the heavy Dirac neutrinos interact with that coherent interaction I talked to you about. But these particles tend to interact axially, and therefore the rate is down by up to factors of 10,000. Now, as I say, this was an optimistic estimate. But you see, to get into this range, you have to get down to less than an event per kilogram per day. Now, if you looked at a more realistic estimate now based on after LEP 1.5, all these curves will go down because as we don't see supersymmetry, the masses get pushed up and the rates get pushed down. And so the question is, can you ever realistically do this? And what's interesting, I think, is that there are ways, and in fact I'm pleased to see that I remember two theorists, one of them was involved in this, fancifully arguing that a long time ago that if experimentalists really did things neatly, you could imagine a detector with both phonons and ions as a particle identification detector. Because we imagine that different particles, when they interact in the detector, even if there are radioactive backgrounds, will produce a different signature in the ion component versus the phonon component. For example, electrons will produce primarily ionization. So beta decay electrons will give a background in the detector, but if you can measure both phonons and ions, you will see far more ions. Whereas slowly moving nuclei, which you might imagine would come from the interaction of WIMPs, will produce much more phonons than ions. Okay? And in fact, that's been demonstrated, which is really kind of in various pretty plots. These are from the LBL group, where a device was instrumented with both a phonon detector and a standard drift ion detector, and a photon source was put in, and this was a sort of the signal that looked on. This is measuring the phonon energy deposited and the ionization energy deposited. And then I think in this case an alpha particle, or neutron source was put in. And the neutrons basically collide with nuclei, and they produce, for the same energy, you see much more phonon content than ion content. And so what is great about this, in principle, is if you can separate this piece from this piece, even if you have backgrounds at the level of 1 per kilogram per keV per day, then you can get to a signal which is much smaller, because you can reduce the backgrounds by a factor of 100 or so by looking only on this channel and cutting on anything in this channel. So from an experiment, perhaps I'm being too experimental here, but this offered hope, at least, and so people can continue to make proposals. And this is this is another figure from the Berkeley group. This is what was currently excluded. This is what a currently running detector at Stanford University, which is not very deep, using this ionization rejection method, hopes to get down to less than the a keV per day, event per kilogram per day. And the argument is, when you go deep underground and get rid of cosmic rays, this kind of veto technique might even allow you to do much better. And this Again, this is an overly optimistic picture from the standard, minimal standard supersymmetric model, but, or supersymmetric standard model or something. But this is the range you're going to have to get into if you have any hope of detecting these things directly, the kind of neutralinos that you might detect at LEP directly if they exist. And to give you an example, here's one of many calculations done of the actual kind of event rates in a germanium detector for a certain range. I was going to show you the supersymmetry range, and I may in a bit, but this is sort of spanning sample space of the allowed space of neutralinos, which might be reasonable WIMPs in their masses. And you see the event rates can get up, if they're lucky enough to have a scalar piece, to 10 to the minus 1. If they're not, the maximum event rates are 10 to the minus 2 to 10 to the minus 3 events per kilogram per day. And so there's a challenge there to do that. I think I'm taking too long, so I'll skip some stuff. But let me just to remind you of the ultimate symbiosis, to show you that you can use particle astrophysics detectors and accelerators together. I want to remind you of at least a piece of history that can be used to rule out, and was used to, the reason people don't talk about Dirac neutrinos anymore as dark matter is because they've been ruled out convincingly. Direct detectors, as I remind you, ruled out Dirac neutrinos as dark matter if they were bigger than 5 to 10 GeV, because that noise cut off. CERN, on the other hand, at LEP, was able to put a bound on the number of neutrinos, the number of light neutrinos. But light, in the case of the Z, is anything less than 45 GeV. And until you get to very close to 45 GeV, the kinematics for a 10 GeV neutrino being produced by Z decay and a massless neutrino are exactly the same, essentially. And therefore, a 10 GeV extra neutrino that might be dark matter would contribute to the width of the Z the same, essentially, as a 0 GeV neutrino would. And therefore, by the fact that there's now clearly, and even then, a constraint on that there were 3 neutrinos that coupled to the Z if they were lighter than the Z, what you could show is that you could rule out any extra Dirac neutrinos with weak interaction rates if they were less than half the mass of the Z. You clearly couldn't say anything if they were greater than half the mass of the Z. But you see, that's exactly what you need. These two compellingly rule out a Dirac neutrino as dark matter, because this tells us that it can't be it has to be lighter than 5 GeV, and this thing says there's no such things in nature. So it's one of those cases where the two things conveniently combine together, and I wanted to show it to you to show that that kind of thing can actually happen. And what's also nice about this is there's no squirming. There's none of that cosmological uncertainty I talked about here. This is definitive. If Dirac neutrinos are the dark matter halo, they would have produced a signal which is easily observable if they were bigger than 5 GeV or 10 GeV, and this is obviously equally compelling. It also works for Majorana neutrinos, but I'll leave it for you to prove as an assignment also. Okay, now that kind of thing, by the way, has been used to then combine these kind of terrestrial constraints with accelerator constraints to produce lots of constraints not on Dirac neutrinos, but on the interesting particle, neutralinos. Okay? And many people have produced plots that look like this that are completely unintelligible. And these are just the people who produce the two-dimensional plots. There are other ones who produce three-dimensional plots. And as everyone knows, it's impossible to read a three-dimensional figure. But these are the mass. I was going to put for you, this is mu and M2, and this is tan beta, and the mass of the neutralino. These are the parameter among anyone who's ever attended a talk on minimal supersymmetry has heard of these parameters, and I thought of putting them here, but I don't think it's worth it. The point is there are constraints on parameter space, and they change each time LEP increases its energy a little bit. There's an auto-generating program here that will produce another paper which will change these constraints. But they exist. The point is, nothing's been ruled, well, particles have been ruled out, and by this I should have said that there has been progress. The limit on the lightest supersymmetric particle, which could be dark matter, was 10 years ago was probably about 4 GeV, and now it's up to somewhere between 20 to 25 GeV, depending upon, but that's for the entire supersymmetric parameter range of tan beta, et cetera, where things used to be able to squeak out. But anyway, I thought going any more would be probably too much detail for this lecture. Finally, the last particle I want to talk about is the axion. I thought I would do an experiment for you here, instead of just talking. So let me do it right now. Okay. What did I just do? Well, I detected gravity. Okay. Trivial, you say. Well, it's not so trivial. Gravity is the weakest force known in nature, far weaker than the force that axions have with matter. How can we detect it? We can detect it because of using coherence again. Let me draw you the Feynman diagram for the experiment I just did. Not that experiment, this one. This is the Feynman diagram of Lorentz interacting with the Earth. What I did here was I did a coherent experiment where I exchanged coherently many gravitons, not just one. And the interaction of each atom in the Earth with each atom in my body by a gravity is unmeasurably small. Okay? However, if I add them up coherently, I produce an interaction which we could all see and we all know about every single day. And that idea was the idea was adapted by Pierre Sakivi to think about axions. Remember when I talked about axions last time, the other thing I mentioned is because they're integrally related to the anomaly, they must, if they're to be relevant, have an E dot B coupling. And it was recognized that, well, axions can have another coherent interaction. The coupling strength here may be very small, but if you have a large enough magnetic field over a large enough volume, you can coherently interact with that magnetic field. And in fact, coherently interact with that magnetic field, turning an axion into an electric field. And since the axion has a mass, into an oscillating electric field, which we otherwise know of as an electromagnetic wave or a photon. So this kind of interaction could turn axions into photons if you coupled things correctly. And even though the axion interaction rate is small, it's humongous compared to gravity. And therefore, it's not too surprising that you might be able to produce an observable signal. This is my favorite of all the dark matter detectors because it's really just a radio, right? I mean, it's just exactly what it is. You have an axion signal instead of the signal from your favorite radio station going on. You have a cavity which is tuned to that signal, so that the size of the cavity and the magnetic field strength in here is tuned specifically to the frequency of that axion field. If you can do it. And better still, you then have a detector which can detect photons, which you tune specifically, look for the right photons. So it's an axion radio. You listen for the axion signal, and what you literally will hear is the music of the spheres if the axions are the dark matter. And that's why certainly it's the most poetic of the dark matter detectors, if not. And what's particularly interesting is that such detectors are being built, and let me just show you, we did a calculation about 10 years ago of the rate, and it's not the kind of thing that people will take lightly. You have to be stout-hearted to kind of consider this. The overall factor, as I said, is 10 to the minus 21 watts. And then in order to get a signal of axion conversion from axions to photons, you just need almost a 10 Tesla field over at least a volume of 200 liters with, this is just a factor that depends upon the tuning of the cavity, with a Q of something like 100,000 or greater, and being able to detect 10 to the minus 5 eV axions. But you can do that in principle, and in practice you are able to do that. And this is an example of the early experiments to show this worked in principle were here, and this is the range, this is axion mass of 10 to the minus 5 to 10 to the minus 6. Remember, I showed you that the naive predictions I gave you earlier for the amount of axion energy which would be left over to produce dark matter is that an axion of 10 to the minus 5 eV might produce an omega equal 1. Those predictions are very loose because they are based on assuming something about the initial value of the axion field, and that could vary by orders of magnitude. But this is a covariant range to look at, and for realistic axion models, this is the kind of coupling strength you expect. And you can see that the present experiment at Livermore is going to scan this range over a very interesting axion range and getting down to at least one of the predicted axion models. And so it's in principle doable, although not an easy task. Okay, that's everything I have to say about dark matter detection. It gives you the kind of idea of there are experiments going on all over the place, and anyone who builds a large underground detector will be looking for any of these particles almost. It's not axions necessarily, but WIMPs and monopoles. And you, therefore, at every conference you go to, will hear talks on constraints on these things. But finally, what about direct detection? I've talked about direct detection of axions, monopoles, and WIMPs, but what about direct detection of astrophysical dark matter? Many people mistakenly say that you have a choice of a WIMP detector or a detector to detect astrophysical dark matter. By that I mean brown dwarfs or something like that, which have come under the name of MACHOs, massive astrophysical compact halo objects. The other possibility for dark matter in our galaxy, while it's rather heretical, might be that there's no exotic elementary particles, but that it's just something that doesn't shine. Okay? Many cosmologists located throughout the halo. As I say, I think it's I think people, as you know, because I write books, I worry a lot about publicity. I think people have said it wrong, because WIMP detectors are certainly also MACHO detectors. You could be absolutely certain that if a MACHO came in this room, as I said, you remember this picture I presented yesterday, you would be able to detect it in WIMP detectors. There's no doubt that if a brown dwarf came through any of these detectors, they would detect them. But in any case, barring the flux is very small, and therefore that's the problem. But so you might want to look for them another way. And what's most interesting has been an experiment, which again represents the kind of symbiosis that can happen between astrophysics and particle physics. Because as I said to you earlier, this required the data-taking capabilities of particle physicists. Is to use lensing. Use literally this. You notice when you lens the Director General by this black hole, I haven't produced a multiple image of him here, but I have affected him. In fact, this, as you can see from here, this part of the image is much brighter than his image is directly. I don't think that's his white hair. I think that's actually, anyway, it doesn't matter. You have to work it out. But the point is, as I showed you, that you can use amplification. If you take a tenth of a solar mass object located in the halo of our galaxy and ask about the kind of, it can multiply image a background source, but if you ask for the splitting that will occur, it's about 10 to the minus 3 arc seconds or less. That's too small to see with any kind of apparatus we have nowadays. But the amplification, as I showed you, can be bigger than 1. So Boden-Paczynski already did the calculation. Remember, I also told you can do a cross-section calculation. Any object traveling along has a little disk around it, inside of which you will produce significant amplification if it happens to traverse the line of sight of an object. So it's literally exactly the same kind of cross-section calculation you do in particle physics. You put these MACHOs out there, and you ask, and each of them carries a cross-section, a disk, and you put a bunch of targets behind it, and you ask, what's the probability that a given target will traverse within a distance of that disk, or within an area of that disk around the object, and you do the calculation, and you find out that the probability of lensing a distant star in our galaxy by an intervening halo object is about 10 to the minus 6 if the halo objects indeed make up the dark matter halo of our galaxy. So what that suggests is you just have to look at a million stars continuously and wait for one to twinkle. Okay? Meaning literally that as this, if you think about what will happen, the signature is quite clear. As this halo object passes in front of the star, it will start to amplify it, and then when it passes across it, that amplification will go down. So the signature is unique. It is a symmetric sometimes, but the canonical signal, as always, canonical signals turn out to be not canonical. But the a priori signal is one which is symmetric, amplified, and most importantly, achromatic. Because one of the good things about gravity, at least the kind of gravity we know and love with the weak equivalence principle at the level we can measure it, is that light of any different frequency will be bent by the same amount. Okay? And therefore, this amplification should happen with the same in the red band and the blue band. That's very important because there are many varying stellar objects in the universe, but many of them tend to vary differently at different color ranges. And this was one of the ways it was hoped to try and reduce backgrounds here. I must say that when I first heard of this proposal, I thought it was absurd. Because not that I didn't think they would see anything. I thought they would see a tremendous amount of stuff. But to be able to extract out real signatures from variable stars was something I never expected this proposal to be able to do. But in any case, it did. But let me just remind you of one important thing. When you do the cross-section calculation, it depends on the number of these disks and their cross-section. Well, it turns out the cross-sectional area depends upon the area of that disk around each object is linearly proportional to its mass. Of course, the number density of halo objects is inversely proportional to the mass. And that means when you do this calculation, the probability of being lensed by a halo object at any time, or the probability of being once lensed by a halo object, is always the same. It's independent of the mass, whether the halo object is a tenth of a solar mass or a solar mass, because the mass drops out. But what isn't independent of the mass is the length of time for this to happen, because a bigger mass object will carry a bigger disk around it. And the bigger disk, the longer it will take for the object behind to pass out of the line of sight. And therefore, the time scale here will depend, in fact, in this case, on the square root of the mass of the object. And therefore, while the probabilities are independent of mass, the actual number of events are not independent of mass. Because if let's say a tenth of a solar mass will produce an event which is 1 month, at any time, being lensed by an object of any given mass is the same. But if you wait a year, you have more probability to be lensed by something which, when the event lasts 1 month, than by something for which the event lasts 1 year. Okay, so the number of events will go up if you measure for a certain amount of time inversely as the square root of the mass. Okay, and that's very important, because that leads to the present constraints and some of the weakness of the present constraints, which lead to the moral I want to leave for this part of this lecture. So what did they do? They looked at there have been various experiments. This is part of the Large Magellan Clouds. So it happens to be a globular cluster in the Large Magellan Clouds. But there's a ton of stars up there. And what's truly remarkable is that they look at a region, different experiments, and actually measure more or less 1 million stars a night, digitize that image, and then measure it the next night and the next night. And that's where the techniques of elementary particle physics came in, because it's a lot of data, because you want to compare the two images. And that's the kind of thing that, as far as I know, was never, that kind of data analysis scale of tens of gigabytes per day was never before done in astrophysics. But it's kind of the kind of thing that particle physics experimentalists can do in their sleep. Okay? So this only became a reality when particle physics experimentalists decided they liked the numbers of 20 rather than 1,000, as I told you earlier, and decided to try and do this kind of experiment. And what is, as you've all seen these pictures, what has been truly remarkable is that then actual several events which have been seen. Gold-plated, real events. This was the first one that was published, where an object in the Large Magellan Clouds was brightened and dimmed, and it happened only once, achromatically, in a very well-defined way. And since that time, the experiment has gone on for several years. And what happened was, after a year, this event was seen, but then not much else was seen. And you could do the calculation, as I'll show you in a moment, what the prediction is. You'd say if these things made up the galactic halo, of course, from a single event, you don't know the mass of the object, because the mass of the object depends how close it was to you and how much off the line of sight. So you see an event that lasts a month, but it doesn't tell you that an object is a solar mass or a tenth of a solar mass, because maybe it was a much bigger object, but the background object just grazed the edge of that disk, got brightened in there. And so you have to look at many things, and you have to get statistics before you can say anything about the mass of machos. But there were a few events seen, and then nothing else was seen for a while, and you could predict that you would have seen, 10 or 20 events if the machos were the full galactic halo density. And all of us particle physicists got all excited because they weren't seeing that many, and it meant that people should still do experiments. And then what happened, and this is intriguingly interesting, is some more events were seen. And suddenly the numbers changed. And here's an example, after the first year and after the second year's run of this data. Here is sort of the halo fraction, the likelihood plots for the halo fraction between 0 and 1, given the number of events that have been seen. This is after the 2-year data, and depends on whether you believe all of these events are actually due to halo events or not, or some of them are due to stuff in the Large Magellan Clouds. But you can see that the mean value is somewhere between half of the halo, and goes up to the entire halo. After 1 year, there's very little overlap between these two plots. This was the curve for the 1-year data, and it was much more fixed on maybe 10% or 20% of the halo, which you might expect to be due to dark objects like white dwarfs or maybe some brown dwarfs. It jumped up tremendously. And I remind you, first of all, that we are just talking about 6 or 8 events. The second thing is that fact that I tried to tell you about earlier. If you ask the naive expected rate as a function of mass, and therefore a function of length of time of the event, the detectors can't detect events that are less than an hour or so this cuts it off here. But what happens is, as the mass gets bigger, the length of the event gets bigger. And that means the number of expected events in a year goes down, even though the raw probability was the same. And what this means is, if you happen to detect one long event, the weight in that distribution will overwhelm detecting, say, 5 short events. And what happens is, as they're looking longer, and then they tend to see because you measure for a longer time, you send an event, when you were measuring for a little while, you would tend not to be able to see long events, and they're seeing some long events, ones that last several months, or even longer. And one such event in this sample, which is what there is in this sample, one such event dominates completely the statistics here. So the fact that they saw one long time event is responsible for probably 70 or 80% of the change from here to there. And that should lead you to realize that it's early, okay? And and the moral I want to leave you with here, and I think this is particularly appropriate given the 500 or so people who attended a talk that was here last week, and probably the 500 people who have written papers on it since then, that only 7 or 8 events that happen in the tail of a distribution are probably preliminary. And it's too early to be definitive that there's something new here. This would work for, say, detectors in Germany or detectors of machos. And so we have the same problem, and unfortunately it appears lately in particle physics and astrophysics, is that there are very few events when you have seen an interesting signal. They're usually in the tail of distributions. And it's very tempting to make definitive statements, but it is far too early to make any definitive statement about the composition of the halo that is made up of brown dwarfs. It's clearly true that there are some dark baryonic objects in the halo because some events have been seen. But how much of the halo that corresponds to is by far not known yet from this distribution. People can speculate all they want, but it's way too early because the statistics are dominated by one single event. Okay? Well, that's everything I have to say about the detection of dark matter. I want to change gears for the last part of the talk. And I want to move to the subject of stars and stellar evolution and how it constrains particle physics. And as I say, I've decided to go into a little more detail here than I would have otherwise because I think it's useful to see the kind of uncertainties that happen in particle astrophysics and also what you can come out of it. The point about stars is that they're remarkably simple systems. They are systems which are in hydrostatic equilibrium, where pressure balances gravity, and the systems last tens of billions of years as a result. And what produces the pressure, we now know, is nuclear burning. Okay? Again, when we learn something new, things change. You all know this fact that some very eminent physicists, before we knew about nuclear burning, did a calculation of how long the pressure gradients in the sun should hold up gravity, and they determined that the sun should be less than 30 million years old. Okay? At the time, that was around the same time as Darwin was coming up with evolution, and the two things conflicted dramatically. Okay? It was a good calculation. The cooling time for pressure, for just the sun to cool down and release its energy, and collapse, would be 30. Your phone is ringing. 30 million years if there was nothing to support that. But we now know that in fact there's nuclear burning, and that allows these things to suppress the inevitable pull of gravity, not for 30 million years, but 30 billion years sometimes. Okay? And just this simple fact that these systems are in hydrostatic equilibrium allows you to do a lot. It governs the entire evolution of stars. And there are a number of different constraints on particle physics one can do. One can talk about the age of standard stars and compare that to the age of the universe, which is what I'll talk about in the rest of today's lecture. The other thing is that any time you put a new energy loss mechanism in the sun, no matter how weak it is, or any star, it can have a dramatic effect on changing that star's evolution. Therefore, we can put very strong constraints on elementary particles by that. And then finally, that one of the things that stars do is emit neutrinos, because neutrinos are emitted very effectively in stars because they get out, and also because the nuclear reactions produce neutrinos, and that's responsible for allowing us the best sources of neutrinos in the world for doing the measurements on neutrinos, in a sense. And so you can use the sun as a source of neutrinos and measure the properties of neutrinos, or you can use supernovae as sources of neutrinos. And I will talk about at least one of these in the next lecture, as well as that. But let me just remind you of the issue of the age of the universe. Some of this I talked about at one level in a seminar here recently, but I will do much different detail here. But I do want to remind you of the issue of the age of the universe that I did talk about last time, I alluded to. It's just simply that the expansion rate of the universe gives an upper limit on the age of the universe. And it's not profound physics, okay? It's described by this equation, okay? Namely, if you have, the universe is decelerating due to gravity if matter is all there is. Therefore, if the universe weren't decelerating, you could do the following simple calculation. A galaxy 1,000,000 light years away is moving away from us at a certain speed. I can measure the expansion rate of the universe. I can work backwards if it's moving at a constant speed and find out how long it took to get there. It's the kind of calculation we could all do, I hope. And we could invert this equation. We could invert this equation here and determine the time that it took a galaxy moving at a constant velocity to move a certain distance. Well, that d over v is exactly the Hubble constant. So for a universe which isn't decelerating, the age of the universe is exactly given by the inverse of the Hubble constant. Okay? But if the universe has been decelerating, then earlier it was moving faster, and therefore it took less time for that galaxy to get as far away from us as it is now, as it would if it hadn't been decelerating. Is that clear? Originally everything started together, now galaxies are apart. They've been decelerating, it took less time to do it than if they'd been moving at a constant velocity. Okay? Well, so therefore you have an upper limit. If you measure the Hubble constant, it gives you an upper limit on the age of the universe. In this case, the upper limit is 12 gigayears for a Hubble constant of 80 in these units. Of course, one could do much better. This is just an upper limit. If you give me a cosmological model, I can give you the exact age of that model. And the simplest is a flat cosmological model, which is matter-dominated. In that case, the age of the universe is not 1 over the Hubble constant, but 2/3 over the Hubble constant. And that is 8 gigayears for a Hubble constant of 80. Now, I argued in the last lecture that the matter content of the universe produced a fraction of the closure density of at least 20%. And if that's the case, therefore, one has a generic constraint that the age of the universe is less than 10.4 gigayears for a Hubble constant of 80, just given the matter content of the universe, okay, even if it's open. If this is all there is, then the universe is no older than 10.4 gigayears for a Hubble constant of 80. And that's the source of the age problem, you see, because the Hubble constant has been measured by a lot of different techniques, and some of these all change with time. But the numbers are now beginning to converge, which may mean absolutely nothing, but it may mean that this is the right number. And you'll see that very different techniques from the ones that traditionally gave low values are now giving in the high 50s. And other techniques, particularly the Hubble Space Telescope measurement, is now down from sort of 80 to 74. And the numbers are getting closer and closer. So it's reason to believe that maybe the number is 65 or 70 here. Okay? And that's true for most of the constraints, most of the Hubble measurements. I do want to give you a historical perspective here and present for you Hubble's original data to show you that this number has changed over time. Hubble, in his brilliance, drew a straight line through this curve. Remember, I gave you that rule of experimentation earlier on in the first lecture, and Hubble did it. He took this data and drew a straight line through it and became famous. And then the straight line had a slope such that the Hubble constant was 500 kilometers per second megaparsec, which gave an upper limit on the age of the universe less than 1 billion year, which again created an age problem in the universe because it was known that the Earth was older than that. And so that was a problem back then. Of course, the Hubble constant has changed by at least an order of magnitude since that time. Not the cosmic Hubble constant, but our measurements of the Hubble constant. So we should remember that even if things are converging now, the number may not be what we estimate they are. But if it is 70 plus or minus 10, then one gets upper limits on the age of the universe of 10 billion years if the universe is flat, and maybe 13 or so billion years if it's open, and therefore, as I put, ugly. And the key question is that consistent with the age of objects within the universe? And that's the question I want to address in the rest of this lecture. And the way you do it is by cosmic dating. You use the fact that the age of the universe is older than the age of the galaxy. Again, a homework assignment for you to prove. And therefore, when one looks at the oldest objects in the galaxy, and I want to discuss the details of this perhaps more than you've ever wanted to hear it in the rest of this lecture. One looks at globular clusters, and one looks at the oldest globular clusters, and I'll talk about this in more detail than I mentioned here, and one tries to determine their age. I like to represent these two different ways of determining the age of the universe by looking at the objects within the universe here and the expansion rate of the universe as two equivalent ways. If you want to think of what you might do if you went to a car race and you arrived late and you wanted to determine how long the race had been going. Okay, there's two equivalent ways to do it. One, you can ask how many laps the cars have done, and you know their speed, and therefore you know how long the race has been going. That's the Hubble constant measurement. Okay? The other way is you can look at cars, Cadillacs and Hondas, and you can ask when the Cadillac pulls into the pit top for the first time and when the Honda pulls in, and you can say, well, I know how fast a Cadillac burns fuel, and therefore I can determine how long the race has been going. And that's the way we do it by stellar evolution, because stars burn their hydrogen fuel at a known rate. And you can ask, when did they exhaust it? And to do that, you look at systems, well, globular clusters, which have the nice property that they're a bunch of stars in a confined system that is very small. And therefore, the dynamical collapse time of that system is very short, and it is reasonable to assume that all the stars in that system formed in more or less the same time, at least on a cosmic time scale. They may have evolved over millions of years or tens of millions of years between them, but not billions of years. So if one looks at this system, one gets a snapshot of a whole bunch of stars of different mass that formed at the same time. And if you plot, and this is the famous diagram of astrophysics, if you look at stars and you're a phenomenologist and you want to look for patterns, you can look at the color of the star and the luminosity of the star and just plot it. And what you find is that this isn't a space-filling curve, which it might have been, but there's order in it. Stars fall only in unique places on this curve, which tells you there's some order behind that system. And in fact, the order is quite simple. By the way, theorists who predict, well, what you measure is not the temperature. I wrote temperature here. You certainly don't measure the temperature of the star, you measure its color. Okay? And you don't measure the luminosity of the star, you measure its magnitude. You measure how luminous it appears, and that will come back, both of those things will come back to haunt us. Okay? I should also say that once again, one should remember that one is dealing with real data, and this is that curve before the data was culled, to make this pretty picture, just so you know. But once you've culled the data, and you hope you've culled it right, you get this curve and you see this pattern. And it was recognized early on that what happens is that hydrogen-burning stars should fall on this thing called the main sequence. There should be a relationship between their luminosity and their color that should fall along that curve. And once stars start to burn helium, they should move off that curve and move here and then do all sorts of other things. And in fact, that then tells us all we need to know to determine the age of these systems, just by using dimensional analysis. Okay, what you need to know is that hydrogen-burning stars exist along here. Also, you need to know that more massive stars, you can calculate, will start higher up on this sequence. Okay? More massive stars will be higher up on this sequence, and lower massive stars will be lower down in this sequence. Okay, well now, let me take a picture of a whole bunch of stars of different masses and ask where they should lie on this sequence at any given time. Well, stars burn hydrogen at a rate proportional to the cube of their mass. Okay? That's, again, you can sort of derive that on simple dimensional analysis arguments, and the actual number is not quite that, but it's close. Now, therefore, how long should it take a star to burn up all its hydrogen? The answer is, it's the total fuel, which is the mass, because the star is essentially entirely hydrogen, divided by the rate at which it's burning the hydrogen. And you see that the time it takes for a star to burn up all its hydrogen is inversely proportional to the square of its mass, making mass, therefore, a very sensitive estimator of time. Namely, the time it takes for an object to go off the main sequence is inversely proportional to the square of its mass. So if I look at a bunch of stars of different masses, at one time I'll see something like this. Why? Well, I'll see lots of stars on the main sequence, but I won't see any more stars above here on the main sequence, because all those correspond to more massive stars, and they've all already burned up their hydrogen, so they will have moved along here. Okay? At a later time, the curve will look like this, because less massive stars will have burned up their hydrogen. And here. And so by looking at where this curve turns off, where you no longer see stars in the main sequence, you get a very sensitive estimator of time. Okay? And that's the idea behind dating globular clusters, is to look for the main sequence turnoff. And here's a piece of data to show you the kind of age estimates that you get for globular clusters in this way. This is based on two different assumptions about the atmosphere of the star, and that I won't go into in the moment. But what you see is this is a globular cluster, this is actual data, and here are curves, theoretical curves, based on the predicted evolution of stars in that cluster as a function of time. These are the isochrones, 14, 16, and 18 billion years, 14, 16, and 18 billion years. And there's two things I want you to recognize about this. Clearly, first of all, the 16 billion year isochrone is the best fit. But more importantly than that, I think, you should see that the shape of these curves gives a remarkably good fit to the data, which tells you that you should have at least some confidence in the theory. Well, maybe. The question is, what would I have to do to the theory to make the shape of the curve be different? Okay? You should always be skeptical. Okay? Maybe no matter how dramatically I change the models and the times, the curve will keep its shape the same amount. And that was, of course, my suspicion when I first saw this. But in any case, if this is true, then the age of these systems is at 16 billion years, and you'll notice that I gave you an upper limit on the age of the universe of at most 13 billion years if it's open, and 10 billion years if it's flat. That's a problem. Okay? And the question I want to address is it a problem? And I want to talk about how one can try and address that. Because here's the naive data that one often sees in astrophysics. Here's the theoretical prediction, there's the data. Well,
excuse me, Larry, I mean, the dispersion is very wide. Does the theory explain why the dispersion is so bigger than the effect?
In principle, yes. I'm going to go into those details a little bit. But there are a number of features here. In particular, stars will have different metallicities, different ion contents, and that'll cause some dispersion. There's also observational error here, which you have to fold in as well. And so it's certainly clear that the fact that there is dispersion is something one should worry about, I suppose. And it's a clear estimate of the kind of uncertainties here, although the clustering here is quite evident. But what I want to do is address what really should be addressed here is the fact that, of course, this kind of fit is irrelevant. Because all of these fits depend upon the fact that there's some theoretical input here, and the theoretical input is based on experiment. Not based on experiment in some cases, based on observation, which is worse, as I told you in the very first lecture. And therefore, there are large uncertainties. And whenever we're trying to constrain something as important as the age of the universe using cosmology, or the existence of a new elementary particle, we have to remember the uncertainties. And this is the object lesson I want to try and show you. As I say, I'm going to bore you to tears in the next 50, or more than I have in the last hour or so, by in the next 5 minutes or so. Well, let's see, when did I begin? At 11? So I have to end in 7 minutes or something. Okay, here are the input parameters that go into that, into the stellar evolution models. There's nuclear burning, there's stellar opacities, there's certain processes in stars that are not understood, diffusion and convection, and defection every now and then, and helium abundances, the abundances of heavy elements, and the equation of state. And I want to go into each of them in a little bit of detail. Not as much as I guess I planned, because I talked more slowly than I planned. Those are just the input parameters. But then there are observational uncertainties. Okay? There are the fact that the theoretical curve predicts the relationship between temperature and luminosity, and neither of those are measured. What you measure are color and magnitude. The color of a star depends as much on the nature of its atmosphere, what it absorbs, as its temperature, just like your color depends as much on what you're wearing as your temperature. And the absolute magnitude of objects is, of course, related. The apparent magnitude of objects is not their luminosity, it's related to their distance. And those are two overwhelming uncertainties. Well, I am going to try and zip through this. The details are not that important, but I want to just give you the idea of the uncertainties. What we looked at recently over 2 years was each of these things and the uncertainties to try and ask, is there a cosmic age problem? Well, nuclear reaction rates have been looked at ad nauseum. I remind you, these stars are very simple stars. These are old main sequence stars in systems with very low metallicity. So they're even simpler than the sun. Okay? And therefore, we understand them at least as well and probably better than the sun in some sense because they're simpler. And because of the solar neutrino problem, you can look at these rates, and these have been measured, as I say, ad nauseum to try and figure out if you can solve the solar neutrino problem. And the uncertainties are in the few percent range, but they're under control at the few percent level. The opacity of stars, their ability to absorb the plasma, to absorb the light at different temperatures, has been determined a lot by people who work in nuclear weapons labs for obvious reasons. And one can get an estimate of the uncertainty in that as a function of temperature by looking at 2 different calculations from 2 different nuclear weapons labs and ask how much they vary. And you can see that for temperatures bigger than about 6 times 10 to the 6 degrees, the deviation is at the sort of plus or minus 1% level in the opacity of plasmas. It gets much bigger at a smaller rate at maybe the 30% level. So in our estimates, in our calculations I'm going to describe lately, we took a 1% uncertainty here and a 30% uncertainty there. Convection. Convection is a case where ignorance is bliss. No one understands convection. So one defines a parameter to measure one's ignorance called the mixing length, which is called mixing length to pressure scale height. And basically you assume some blob moves a certain length and then deposits its energy. And you say, let me call that length the mixing length. And try and put that as a parameter in your models and fit them to the sun to get the correct, at a given age of the sun, to get the correct size and luminosity. And when you do that, you get a range for that parameter, which really measures something which is not physical. But as I say, for lack of time, I just want to indicate, however, this heartened me at least. I could vary the mixing length when I did my calculations over the range which was allowed sort of in the sun, or people use for models. And hearteningly, you see that the curve actually you can make the curve disagree with the data, which gives you faith. Because if you can actually change a parameter and make the curves disagree with the data, it means maybe the agreement of the curve with the data actually is telling you something. Okay? But there's some uncertainty there, and we plug that in. Helium diffusion has been a subject of great interest recently because of the solar neutrino problem. It used to be a non-standard process. And by that I mean that John Bacall didn't include it in his codes. Okay, literally, I'm not being facetious. What is determined to be standard in the sun is very different than what's determined to be standard in the standard model. What is standard is the physics that those people who've done codes include. And there are many non-standard things which we know exist, such as rotation. Okay, but it's hard to model a three-dimensional object that's rotating, and therefore, until recently, that has not been included in stellar evolution codes, and it's called a non-standard process. It's not non-standard because it doesn't happen. It's non-standard simply because it hasn't yet been included. Okay, it's very important to realize that. Diffusion was such a non-standard process until it was included. And what was important about this, and John Bacall will show many graphs, and as he should, that if you look at one of the best probes of the inside of the sun, helioseismology, which measures the vibrations of the surface of the sun and tries, just like when we search for earthquakes, to determine the nature of the inside of the sun based on the motion of sound waves in the sun. Before diffusion, this was the difference between the calculated speed of sound as a function of radius of the sun for solar models versus the actual measured number from inverting measured helioseismology data. And what you saw was that the agreement was very good, even in the old days. It was good at the 1% level. Right through to very close to down to near the core of the sun, the deviations of the predicted standard solar model and the measured sound speed in the sun was good at the 1% level, which gave people faith that there was not something absurd happening, and was one of the arguments that the solar neutrino problem might relate to particle physics. But you now see that including diffusion makes the agreement even better. In fact, actually, I got a more recent plot off John's website recently. which shows that the agreement is still even better. And so diffusion, this is now the model versus minus the sun versus the sun, and you see this is the new best standard solar model, including the new opacities and new diffusion and all, and you see the agreement is very good compared to playing games. And so that means maybe we should include diffusion. One should point out, however, that there are other places other than the sun where diffusion makes the agreement with data worse. So diffusion is not a universal thing. It may happen in the sun, it may not happen in all stars. And I just wanted to point out, these are lithium observations. And the point is that this is the data without diffusion, and this is the data with diffusion, and I even have chi-squared analyses here, but you can see that diffusion makes the agreement much worse with the data. So what's clear is diffusion happens, but it doesn't always happen by the same amount in the same kind of stars. And so in our estimates, we assumed a diffusion rate which varied between 30% and 1.2% of the rate which best fits the sun, based on the fit to other stars. Okay, well, I think I've done enough of this. I have more, but I don't want to keep you too late. You get the idea. And what we tried to do in this analysis, and I really don't have time, unfortunately, for the real nitty-gritty details that I'd hoped to talk about, is try and include all those input parameters and do a realistic estimate of the uncertainties to see if there was an age problem. The biggest uncertainty comes not from any of those input parameters, but from an observational parameter. Namely, to normalize the color luminosity curve, you have to know the absolute luminosity of at least one of those stars in that curve. And traditionally, where you determine that is, here we go, is right here, from the R. Lyrae stars. Because, first of all, you see, they lie on a horizontal branch, and therefore they're all the same luminosity, and therefore there's not that luminosity uncertainty if you're trying to pick out any other species. But if you can know the absolute luminosity of one of those guys, then you can know, in your predicted thing, you can fit it to that, and then you can fit the rest of your curve. Otherwise, it slides up and down, depending upon the distance, okay, and the absolute luminosity. And that, the distance, the scale associated with R. Lyrae stars and their absolute luminosity is the major uncertainty that comes in determining the age of globular clusters. So let me just show you the results of our Monte Carlo analysis and conclude with the question of whether there is an age problem and leave you with another moral. Here's this result which I have called quantitative impressionism. These are 1,000 models run to fit the age of the 17 oldest globular clusters. And what I've left out is the one thing which relates to the distance of R. Lyrae stars, which is the overall largest uncertainty. And as this number changes, the distance scale associated with R. Lyrae stars into globular clusters, or the absolute luminosity of R. Lyrae stars, changes. So if I pick a luminosity of R. Lyrae stars, I can normalize all those curves, and I can run 1,000 models, and I can fit the ages, and I get some uncertainty in each of those ages, and then I change it, and I get this, and I change it, and I get that. And the question is, what is the distribution of uncertainty of that quantity? I was going to show you, but we analyzed this extensively and argued that the uncertainty in this quantity was Gaussian. All of the estimates agreed within their error bars, and the uncertainty in here was Gaussian. So to determine a distribution of ages, we were able to take this figure, pick an R. Lyrae absolute magnitude in this range by a Gaussian, randomly, which would put us on one of these plots, pick one of these randomly, one of these models, pick the uncertainty of the age randomly with a Gaussian here, and write that number down, and then repeat it as many times as we wanted to do, and from that one could get a distribution of ages. And here's what we produced as our given this uncertainty in R. Lyrae stars, for the age of the oldest globular clusters. And you see it's peaked around 14.5 billion years, but what's more important, and we felt for the first time one could give some realistic estimate of something like the 95% confidence level for what the lower limit is on the age of globular clusters, given the uncertainties. And we came up with an age of a lower limit of 12.1 billion years. Now the question is that compatible with, say, 10.4 billion years for a Hubble constant of 80, even for an open universe, or 10.4 billion years for a Hubble constant of 60 or 50 for a flat universe. 60 for a flat universe. is 12.1 compatible with that number? We tried to seriously analyze the errors, and we argued that there potentially is a problem here. And I want to remind you how serious this problem is. If this is incompatible with that, you are driven to one and only one way out, which is to add a cosmological constant to nature. Because a cosmological constant will slow down the cosmic deceleration, in fact, produce a cosmic acceleration, and change all those age estimates. You can actually do it. And you can find, for a Hubble constant of 60, the universe can be as old as 18 billion years, but for 80, it can be as old as 13. It's the only way to make it that old, if the Hubble constant is 80. So this is a serious problem. And we tried to analyze it seriously. And there's now been recently a bigger age problem having to do with old galaxies at high redshifts, which I was going to discuss the analysis of, but I won't. I want to just get down to show you what you're dealing with when you're dealing with cosmology. Just when you thought it was safe to go back to worry about other things because this problem was nailed down, the distance scale to the Large Magellanic Clouds has changed, some people have claimed in the last month. Okay? And I want to describe that. And it involves the one thing that I think everyone thought was well known. When we measure the distance to distant objects, we measure the closest distances by parallax. By taking the Earth when it's on one side of the Sun and looking at a nearby star, and the Earth 6 months later when it's on the other side of the Sun, and just doing what surveyors do. There's nothing exotic about it. And it's supposed to be geometry, and we're supposed to know how to do geometry. Well, recently, people have argued, two people whose names are easily remembered, Feast and Catchpole, have argued in a paper which has been submitted, and I think has been accepted at monthly notices of the Royal Astronomical Society, based on a subset of the data that just came out from a satellite experiment, the Hipparcos satellite, which is designed to measure parallaxes, good to almost 10 to the minus 3 arc seconds, I think. Okay? And they took, not the entire data set, but a small sample, turns out 26 objects, and they looked at those and looked at Cepheids, variable stars, which are the things which you then look at in distant objects and try and, from the ratio of luminosities, apparent luminosities, determine the distance. Okay? So Cepheids are one set of standard candles because Cepheids of the same variability are supposed to have the same maximum luminosity, and therefore you can use them. And they argued for nearby Cepheids, and then looking at the Large Magellanic Clouds, that the Large Magellanic Clouds is 10% farther than people, and that anyone had, well, not anyone, but then had been estimated before. That has the following effect. That says that everything in the universe, based on Cepheids, is 10% farther than it was before. And that means that measurements of Cepheids in Virgo with the Hubble Space Telescope, which were done, will give a Hubble constant which is 10% smaller than was claimed before. So therefore not 74, but 67. The universe gets older. But it's even better than that. It says that stars are farther than we thought they were in any system, which is normalized by variable stars, Cepheids or RR Lyrae. And that means they're brighter, because if they have the same apparent luminosity, they're actually brighter. If they're brighter, they're burning hydrogen faster and they're younger. You do the calculation and you find out, in fact, he used our data, and you find out that they're 30% younger. And therefore, the peak of the distribution that we spent so much time trying to determine by our careful analyses is really not 14 gigayears, but 11 gigayears, which you'll notice is outside the range of our 2 sigma confidence limit, which we so carefully tried to determine. Now, this is either right or wrong, probably. The question you have to ask yourself is, which do you prefer, this to be right or that to be right? Well, even cosmology is not done by preference, although lately it has been. I know at Princeton they run meetings where they have votes on what things should be. But what I want to point out is I'm actually willing to believe that this result is wrong. You heard it here first. I don't believe this result, even though it solves all the problems. I don't believe it just because I spent so much time trying to show there was a problem. At this point, I'm skeptical. The reason is we actually argued that things were Gaussian because there are many independent estimators. These are RR Lyrae distance estimators to Large Magellanic Clouds. I even have a better bit of data to show you. And I realize I've gone over time, but I will end in 1 minute, if I can find this piece of data. Convince you of what I wanted to show you. Here we go. These are distance estimators to the Large Magellanic Clouds, and this is how they sort of cluster in this what's called the distance modulus. And if the new result is right, the distance modulus to the Large Magellanic Clouds is 18.7, which is right at the edge of everything that's been measured before. Now this is interesting. If it's right, that's remarkable. It means everything that's been measured before is wrong, which could be true. It is, as I said, cosmology and astrophysics. There are systematic uncertainties that can dominate all observations, and we should be prepared for such a thing. But some of them come from physics, from simple physics. One of them in particular, which I find particularly compelling, is to look at supernova 1987A, which is in the Large Magellanic Clouds, and look at the rate at which the shell is expanding. And you can do careful analyses of how fast that shell should expand, and you can actually see it, which is kind of remarkable. With the Hubble Space Telescope, you can see the inner debris actually expanding in size, physically. And you can say, given the physical size spread in arc seconds and the speed at which it should be expanding, I can therefore calculate how far away that object is. And that was one of the estimates that's here. And if the new result is right, that estimate is also systematically wrong. By not a huge amount, but a significant amount. But it's just one. There are 4 other different estimators. They all cluster, and they were all in agreement. So at this point, as much as this would be a wonderful way of solving the age problem, it may or may not be right. But I want to leave you with that moral, at least, as an object lesson. In any time you use particle astrophysics to constrain, or astrophysics to constrain some fundamental quantity like the cosmological constants, we have 2 choices with the age problem. Either systematics can overcome anything you do, no matter how careful you are when you try and make a constraint on particle physics, which has been a historical truth. Or, if my hunch is right and that's wrong, and it may not be, if that's true, if there really is an age problem, then this is a dramatic example, probably the most dramatic example I know of, where particle astrophysics actually directs particle physics. Because if there really is an unambiguous age problem, which we will know by these kind of measurements as they're improved over the years, when we measure the Hubble constant, which we will do in the next decade, to 10 or 20% at least, and when we measure these remaining residual uncertainties like the distance to the Large Magellanic Clouds, using parallaxes and other things, we will be able to say if there's an unambiguous age problem. And if there is, then you might be driven to a cosmological constant, which would by far be the most dramatic new input, far more interesting than elliptic quark into particle physics, I would venture. Okay, so in the last lecture here, what I'm going to do is show you how to constrain some properties of exotic particles, including neutrinos to the extent that they're exotic. And then I want to return at the very end to the thing which created the particle astrophysics connection, which is Big Bang nucleosynthesis, and look at that in some detail and ask, is there another problem in cosmology? Thank you. Sorry about that.